and v are elements of a vector space V, so we have vectors in the vector space, then u plus v is also in V. That's a property of vector spaces. And what's that property called? What? Nobody? Closure? Closure or closed under addition? For any vector space V, is 0 in the vector space or not in the vector space? It is always in the vector space. Yeah. And you can get a free point for question 3. There we go. Okay, so vector space is just any set of stuff that satisfies these 10 properties. So Rn, R2, R3, R anything always satisfies these 10 properties, but there are other sets of things that satisfy these 10 properties. So the first, I don't know, several are sort of the most classic. Like those are the things you look for first if you want to know if something's a vector space, because you'll see a failure earlier. But all 10 of these have to be true for something to be a vector space. But from those 10 axioms, there's a few more facts about vector spaces. And then once you know you have a vector space, something that's a subset of that vector space is easier to prove that it's also a vector space. It's called a subspace. And it only has to satisfy 3 things. If it lives within a vector space and it satisfies these 3 properties, then it's also a vector space. So the 3 properties are: it has to contain the 0 vector. That has to be true of any vector space. And it's closed under vector addition and closed under scalar multiplication. Okay. So closure means that if 2 things are closure under addition means if you have 2 elements in the space, when you add them together, you get another element in the space. And closure under scalar multiplication means if you have an element in the space and you scale it by a scalar, then the result is still in the space. So we'll do several examples, try to make this clearer. All right, so this is just a set. I've just described a set V. It's the set of all vectors A, B, such that A and B are real numbers. A is positive, B is positive, and B is smaller than A. So try to, based on this description, just list some vectors in V. Somebody give me one vector that's in that set. 0, 0, yes. Yes, because A is bigger than or equal to 0. B is bigger than or equal to 0, and B is less than or equal to A. So 0, 0 satisfies. Yeah, I would like another one. 0, 1. No, why not? Yeah, because B, the second entry, has to be smaller than the first entry. So 1, 0, yeah. 1, 0 works. Give me a couple more. 5, 4. 6, 2. Great. Yep. No, we can't. Sorry, we can't do negatives because there are restrictions on A and B. But they don't have to be integers. We could have like 12 pi, right? It can be real numbers. All right. If U and V are both in V and you add them together, do we get something that's still in V? So we could check by adding a couple of these that we chose. We can check a few. Like if I add 0, 0, and 5, let's do 1, 0, and 5, 4, right? If you add those together, you get 6, 4. Does 6, 4 satisfy the properties of the set? Yeah. Okay, so that one works. What if I add 6, 2, and 12 pi, right? I'm going to get 18, and 2 plus pi, that's like 5-ish. Does that satisfy the properties of the set? Do you think if I pick any two vectors, u and v, and add them together, I'll still satisfy the properties of the set? Yes. Yep. So we have not proven it by doing a couple of examples, but we've sort of convinced ourselves like, oh yeah, this is always going to happen, because if both b's are smaller than both a's, then when you add them together, the sum is going to be smaller. So that should work. So yes, if u and v are in the set and you add them together, you land back in the set. All right, but now I want to find a specific vector v and a specific scalar c. C can be anywhere in the real numbers, so that when you multiply your scalar c times v, you're no longer in the set. The result is not in the set. So pick a vector v from my several that I have to choose from. Let's pick 6, 2. 6, 2. I want to scale it, multiply it by a scalar, so that my result is not in the set. Any negative, yeah. Right. So C can live anywhere in R. It doesn't have to satisfy any of the conditions of V. Scalars just are anywhere on the real number line. So when I do that, I get -6, -2, which no longer satisfies the definition of the set, right? Because my A and my B are negative. That is not an element of V. So is V a vector space? No, I just failed one of the key 10 criteria to be a vector space. You fail one, you're not a vector space. You have to meet all of the 10. So this is a no. So very quickly, I'm just going to talk through what the 10 properties are. So the first one is closed under addition, right? So we said that one was a check, but it was not closed under scalar multiplication, which is six, right? Not closed under scalar multiplication. And then there's lots of other properties. Addition has to be commutative and associative. 0 has to be in the set, and every element has to have an additive inverse. Closed under scalar multiplication. The distributive property has to hold. Same distributive property again. Associativity under multiplication, and there has to be an identity element under scalar multiplication. So there's 10 properties. You just check them one by one. But the most common things to fail are your closure, addition, and scalar multiplication, and the 0 element. Those are like the 3 most common to fail and easiest to check. All right, so here's another one. I've got H. It's a set of vectors that look like A, B, 0. A and B are just any real numbers. So let's list a few vectors in H. Right. 1, 2, 0. 9, 10, 0. Does that pattern hold? Or do the first 2 entries always have to be differed by 1? No, they can be anything. Let's say -5, 3, 0. That's good. All right, is H a subset of the vector space R3? Do all the elements of H live in R3? Yes, so that's what a subset is. Like, does it live inside of R3? So yeah, I could list elements in H that satisfy this all day, right? And all of them are 3 entry vectors. So they live within R3. That makes it a subset. So we haven't answered the subspace question yet. It's just a subset, which means it lives inside R3. Now, if it's a subspace, that means that it's a subset that is also a vector space. So there are 3 things we have to check to determine if it's a subspace. It has to satisfy, is the 0 vector in it? Is it closed under vector addition? And is it closed under scalar multiplication? If it satisfies these 3 criteria, and it's a subset of a vector space, then it is also a subspace, which means it's a vector space itself. All right, so is 0 in my set H? Yes, because you just choose A and B. A and B are 0 is a real number, so this is a yes. Is H closed under vector addition? Yeah, so you could check a couple, right? Like add these first two. 1 and 9 gives you 10, 2 and 10 gives you 12, 0 and 0 gives you 0. So because every element of the set has a 0 in the last spot, if you add any two together, you're going to get a 0 in the last spot. So this is going to satisfy closed under vector addition. How about closed under scalar multiplication? Yes, so no matter what vector I choose, I can scale it by anything I want, and I'm going to get real number 0, right, which makes it part of the set H. So this is yes. All right, so I managed to answer yes to all 4 of these questions, right? It is a subset of the vector space R3. It contains a 0 vector, closed under vector addition, closed under scalar multiplication. That means H is a subspace of the vector space R3. Okay. And if you're a subspace, that means it's also a vector space. So it actually, we only had to show it satisfied 3 properties of vector space, but it actually satisfies all 10. You don't have to show it if it's a subset of a known vector space. All right, there's another way to prove something is a vector space. Rather than going through all 10 properties and saying like check, 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 and having to do that for 10 different properties. If you can write your set as the span of elements from a known vector space, then it's a vector space, okay, or a subspace. All right, so I want to write H as a space as the span of some elements from R3. So my goal is to say H is the span of some vectors in R3. So whatever I put in here needs to live in R3. And when I put scalars on them and add them together, I get A, B, 2A plus B. So I've got 2 different parameters here, A and B. So I'm going to use 2 different vectors. So my first one would be like for A, for my A parameter. So I would have a 1, 0, 2. Those are the coefficients on my A's. My second vector would be for my B's. So I would have 0, 1, 1. So I'm going to write a little bit more here to sort of explain how I got that. So if I were to use my A's as parameters, remember parametric vector form. So my A and my B are my scalars. And then I have my 1, 0, 2, and my 0, 1, 1. Now I have 1A and 0B. That's my first entry. And then I have 0A and 1B. That's my second entry. And then my third entry would be 2A plus B. So A and B are my scalars, so that's what the span is. The span is all linear combinations, right? And the definition of a linear combination is when you put some scalars on the vectors and add them together. So because I was able to write H as the span of some vectors from R3, and I know R3 is a vector space, then H is also a vector space. Call it a subspace of R3.